Hi, my name's Nick Barker, and this is a technical programming talk on something called the single source of truth principle. And in a wider sense, it's an exploration of what a source of truth is and how mistakes or errors with sources of truth are one of the most common causes of bugs in software. So if you can understand the way that sources of truth work, and when you're creating multiple sources of truth, it will lead you to writing much higher quality software, I think. So just a summary of the talk, if you don't have time to watch the entire thing. The principle's very simple, right? It's just that you should only ever have one copy of mutable data, as in data that changes, data that you can modify, right? Because if you have multiple copies of mutable data, i.e. multiple sources of truth, eventually you're going to modify one of them and forget to modify the other, and now you have a bug because you have data that's out of sync, right? One of the variables maybe contains an old copy of something. There are a million ways in which it can go wrong. It's worth mentioning that it is okay to have multiple copies of immutable data, that is, data that doesn't change, but it's important to mention that it won't necessarily stay that way in the long run. Eventually, at some point, another developer or just you in the future is going to come along and decide that one of those pieces of data should change, and now you have a bug again. So overall, if data is going to change, you should only ever have one copy of it, and that's one single source of truth, right? So just some background so we can kind of understand what the fundamental idea behind a source of truth is and why it's such a common cause of bugs. If we look at an analogy in the real world, if you've ever moved house before, you'll know that it's a huge pain to have to update your address in all of the different places that send you mail. Banks, governments, services, delivery, apps or services, whatever. I actually have a pile of mail at home in a drawer in my house that I need to go and return to sender because it's been incorrectly sent to me when they meant to send it to someone who used to live at my address but since moved somewhere else, right? You've probably received mail. If you've ever lived in a rental, you've probably received mail that wasn't addressed to you because someone forgot to update their address. It's a huge problem that affects basically everyone on Earth. And the reason that this happens is because we don't have a single source of truth for our personal data, right? We have multiple sources of truth that all these different services rely on. And so we need to update all of them, and eventually you forget to update one of them, right? Conversely, this is another interesting thing with the concept of sources of truth. Sometimes we actually want multiple sources of truth, right? Because say if I go over to my friend's house and we want to order pizza, and I open up like a delivery app and I'm inputting my friend's address to order pizza, I don't want that to become the single source of truth for my address. I don't want my new credit card sent to my friend's house. I don't want to be enrolled to vote in my friend's area, right? So sometimes we actually want multiple sources of truth. And this is getting at kind of like a deeper problem, which is like humans are very good at discerning when things look different but are actually the same, and when they look the same but when they're actually different, right? We are very, very good at those subtle distinctions. Computers are not good at that type of thing. They're very literal, and there are very clear rules about when things are the same and when they aren't, right? They don't have any of that subtlety. Just to illustrate the point, if you give the two pictures on the top left to a child, they'll probably be able to tell you that they're both dogs, right? They look very, very different from a visual perspective, but they represent the same concept. We understand that they're the same, even though they look different. Whereas in the bottom right-hand corner, you'll see that there's 4 blueberry muffins and 4 chihuahuas, right? And we understand that muffins and dogs aren't the same thing, even though they look very similar. And this is, one of a very large number of examples where AI tends to confuse things that look similar but are actually very fundamentally different from one another. And this is what I'm talking about. What it comes down to is when you're programming, you have to remember that the computer doesn't understand that different memory is representing the same data, representing the same idea, right? The computer doesn't understand that just because there are two values in two different places in memory that are identical, it can't know that it has to keep them in sync for you, right? You have to manage that in your code yourself, and that's where bugs come up. So I'm just going to run through a lot of examples of source of truth bugs, and hopefully you can start to see how pervasive these issues are and how, if you carefully think about them and if you're aware of sources of truth, it can lead to building better software. So the first and one of the most obvious examples is the mistake of storing derived data, right? So when I'm talking about derived data, all I'm talking about is you take some piece of data, you perform some kind of calculation on it, and you get a result, right? But the result is entirely dependent on the input, right? You get the same input if you get the same output if you have the same input, right? So in this case, on the right-hand side, you can see we have a list of 5 numbers, and we've calculated the average, right? The mean, which is 4.6. So this is accurate right now, but if we save the average, if we save the derived data, we've actually made the mistake of creating multiple sources of truth. So there's a bug case, obviously, which is you add a new value to your list. We've added 7 here, and we've forgotten to update the average, right? Because we had multiple sources of truth, we ended up with one of them becoming out of date or incorrect. And you could say that this was a mistake from the developer, or it's operator error, whatever you want to call it. But I actually disagree. I think this type of bug is inevitable with multiple sources of truth. I think it's basically impossible to prevent this kind of thing from happening eventually, right? We can't rely on just like experts always doing the correct thing. So how do we solve this problem in a way that we prevent us from making mistakes, prevent operator error? And the solution, of course, is calculating derived data on the fly. We never actually save the average anywhere in memory. Instead, when we need to use the average, we provide a function that calculates the average on demand, right? And if we do this, it means that the derived data is always going to be recalculated based on the single source of truth. That's the important thing here. We have a single source of truth for our numbers, and our average we can compute and then discard the value after we've finished using it. And we can prevent any case of operator error in calculating the average here. It's worth mentioning, just as a caveat, that sometimes calculating the derived data is very expensive. Say we had like 200 million numbers in our list, we probably wouldn't want to recalculate the average constantly. But that leads you down the path of having to do caching for performance reasons, and we all know that caching is very hard. There's an adage which is there's only 2 hard problems in computer science: cache invalidation and naming things. And I'm not going to go down the rabbit hole of talking about caching for a whole hour, but I will say one of the interesting things that you might not have thought of is that the reason that caching is hard is because it fundamentally forces you to have multiple sources of truth. The whole point of caching is that we keep multiple copies of the same data because the derived value is expensive to calculate, or it's far away in the world and takes a long time to retrieve, that type of thing. It forces us to have multiple sources of truth, and as a result, we have all the bugs that come with multiple sources of truth. So the next thing I'm going to talk about is absolutely fundamental to programming with modern programming languages. I'm going to talk about the way that variables and values and references are passed around in code, when they're copied, when they're passed. And if you work professionally as an engineer, you will encounter this type of thing, these mechanisms, hundreds of times every day. It is incredibly important to understand precisely how they work and when you can end up with multiple sources of truth and when you can end up with single sources of truth. And I apologize, this is going to be a little bit abstract and dry, but it's really important to understand how each of them work. So the first thing I'm going to talk about is pass by value, right? So most languages, when you call a function and you provide an argument to the function that's a primitive value, say a number, for example, the number is actually copied into the function, right? So you have 2 copies of your number, right? the copy outside the function and the copy that gets passed in as the argument. As a result, you might not have thought about this before, but passing by value, in this case, copying the value into the function, actually creates multiple sources of truth. And this is a common bug that very new engineers can fall into. If you have a look on the right-hand side of the screen, we have a function called increment, which takes a number as an argument and increases it by 1 and then prints the value to the console, right? So lower down, we define our value as 1. We call increment with our value, and we can see that 2 is output to the console. But then if we log our original value, we can see it's still 1, right? And that's because we have 2 copies. We have 2 sources of truth. This is one of the most obvious examples. If you're an experienced engineer, you probably very rarely make this mistake now, but it's important to be aware that it exists, and it is tricky for new engineers. So getting a little bit more... Oh, actually, sorry. Another thing to mention that's a little bit more obscure that you might understand intuitively but might not have actually actively thought about is that pass by value is also used when we're putting values into arrays or into properties on objects, for example. So you can see I've defined a value of 1 here, and then I've inserted it into an array, and I've added it as an property to an object, and then I've incremented my value. You can see that the original value increases to 2, but the value in the array is still 1, and the object property is still 1, right? In this case, we actually have 3 copies because we copied the value twice to insert into our array and into our object. So it's important to be aware of when we're copying these values and when we're creating multiple sources of truth. The next thing I want to talk about is pass by reference, right? So most languages, if you're passing something that's not a primitive value, say an array or an object, right? We are actually passing a pointer into a function to that array or object, right? And as a result, the function can actually access exactly the same array, for example, as the code outside the function. We have a single source of truth for the address that our pointer is pointing to. The memory of the array is our single source of truth, right? So you can see on the right-hand side, we have this generic kind of create config function. All it does is take an array of values and returns you an object which has those values attached, right? So we create our values array with 1, 2, and 3. We create a config using those values, and then we call push on the values, and we push the number 4 into the end of the array, right? Because push actually mutates the array, it modifies the data, right? You can see that the config values have changed as well, right? Unlike the primitive value that was passed by value before, we're passing the array by reference, which means that inside the function, we're referring to the same array as outside the function. So we have a single source of truth here. But here's the tricky part, and this is something that even a lot of experienced engineers forget about or don't really understand. The pointer that we pass into the function is actually passed by value, right? Which means it's copied into the function. So if we follow the pointer and mutate the array, in this case using push to add a value to the end of the array, sure, we have a single source of truth. But look at the last 2 lines, right? If we reassign our out of values array to something new, what we're actually doing is we're modifying the values pointer to point somewhere else. And see how the config values is still the old array? It's not 1 and 2, it's 1, 2, 3, and 4. And the reason for that is the pointer was actually copied. So despite the fact that we only have one array, we have multiple sources of truth of pointers that point to the array. We have 2 different pointers, right? And that can be a big source of confusion. If you reassign your array to a different value, you're not actually modifying the array or the pointer that was passed into the function. Then we have a third kind of scenario, which adds another degree of complexity to the way that values are passed around, and that's closures, right? So languages that support lambdas, anonymous functions, callbacks, that type of stuff, an increasing number of languages support these types of things because functional programming is kind of coming in. So in this case, all a closure is a function and its all the variables that it can see because of the scope that it was defined in, right? That might sound a little bit abstract, but if you look on the right-hand side, you'll see what I mean. See how we define value on the first line, and our increment function from before now doesn't take any arguments, right? All it does is increments this thing, this value variable. So if it's not an argument, how can it see the value variable? It's because it's in a closure, right? The function was defined in the same scope that value was defined in, and so it has visibility of our value variable. Right, so our increment does the same thing as before. It increments value and then prints it out. And you can see here, if we call value and we increment value, right, we get 2. Right? But then if we reassign our outer value to 5, right, and then call increment again, we get 6, right? And it's because our outer value and the value being referred to inside increment are precisely the same thing. It's a true pass by reference in this case. So we don't have a copied pointer or anything like that. So if we were to assign our outer value to, undefined, and then we call increment, we would get either an error in some languages or, bizarre behavior in something like JavaScript. So yeah, that's something to think about as well. You have pass by value, passing references by value, as in copying the pointer, and then you have closures where you actually have a really the same source of truth. And it's worth mentioning, as an aside here, there is a special place in hell for the person who decided that JavaScript should have a mixture of mutate in place and copy and return style functions. And what I mean by that, if you look on the right hand side, we have this process elements function, right? And it takes an array of elements, and all it does is it pushes 5 to the back of the array and then sets elements using this concat function, which essentially just sticks 2 arrays together. So you can see we define our array that has elements 1 and 2, and we call process elements. We push 5 to the back of the array, and then we set elements with this concatenation with this other array that just has 10 in it. And you can see there that elements is now 1, 2, 5, 10, right? But if you look down the bottom, you can see that our outer elements array is 1, 2, and 5, right? And the reason for that is push followed the pointer and mutated the memory there. So it's referring to the same array. Whereas when we called concat, we had to reassign the elements variable, because concat makes a copy of the array and returns it, right? So now we have 2 different arrays. So I've seen countless bugs with people misunderstanding mutate in place versus copy and return, these 2 different styles. And one of the reasons that this happened is because we have this long-running fight between object-orientedness and functional programming. In functional programming, people often think, you should be always making a copy. Data should be immutable. You should make a copy whenever you want to change it. Whereas in object-orientedness, you want the array itself to have a state and be able to mutate itself with functions. There's a lot of different stuff going on, but I think the main thing is you just want to try and maintain a consistent style. So I know that seemed like a lot, and in terms of the solutions to creating bugs accidentally by misunderstanding pass by reference, pass by value, that kind of thing, there unfortunately isn't really a solution. The only way to protect yourself against accidentally creating multiple or single sources of truth erroneously with the variable mechanisms in programming is just to really understand how they work. It's incredibly valuable to deeply understand how your language of choice moves values around, where it copies them, where it uses a reference, where it copies a reference, that type of thing. Take special care with function arguments, closures, and anonymous functions. They're very easy to shoot yourself in the foot with. And one last little tip here. One thing that can really help is just adopting a consistent programming style. So when I said that there's a mixture of mutate in place and copy and return in JavaScript, you could decide to only use one or the other of those things. And that way you wouldn't accidentally mix them together and create an unintended multiple source of truth bug. So pointers are a wonderful way to create these types of bugs, and I'm not going to go all the way down the rabbit hole on this because there are some fantastic talks, lectures, articles about all the ways that you can screw yourself over with pointers. But I just want to point out that languages like C and C++ allow you to use raw pointers, right? Which are just unsigned integers that point to an address in memory. And you might not have thought about this before, but as soon as you have multiple pointers to the same data, you have multiple sources of truth. And as a result, you have all the bugs that can occur as a result of having multiple sources of truth, right? If we think back to the analogy about moving house that I made at the beginning of the talk, this is exactly like that, right? A pointer is essentially an address, and one of your pointers runs out of space because it's a string or it's an array and it needs more length or something, and it reallocates yourself, it moves house, and now one of your pointers is pointing to the wrong address. It's extremely easy to create bugs in this type of situation. So there are a couple of solutions, that have been attempted. You can use smart pointers, which are like a wrapper around pointers so you can access pointers indirectly. You can update the pointer internally without having to update all of the places where it's used. They can keep track of the number of references and automatically deallocate the memory for you, that type of thing. You can use in-memory databases or some approach like that, where instead of storing a pointer to an object, you instead store like an ID, and you use that ID to look up the object in an array or in a data structure, that type of thing. There are alternate memory management approaches that allow you to do low-level memory stuff without necessarily using raw pointers. RAII is a common thing in C++, and the Rust borrow checker is like a different type of attempt to fix some of these problems without having to expose raw pointers and all the bugs that comes with that. But the main thing to just remember here is, again, you might understand that two pointers are supposed to be the same. They're pointing to the same thing, but the computer doesn't, right? The computer has no idea that two regions in memory, just because they have identical values, it doesn't understand that they're supposed to be the same. So remember that you have a lot of context that the computer doesn't, and you have to be aware of when you're assuming something that the computer doesn't know. And the last big thing that I'm going to talk about in terms of sorts of truth bugs is the rise in prevalence of stateful libraries, right? And I think this is actually one of the biggest drivers of bugs and decline in quality in modern software. So programming, in the modern world relies on like thousands and thousands of libraries. If you've ever worked in front-end web stuff, you'll know that it's a meme that you have a 10 gigabyte node modules folder for an application that has like 2,000 lines of code, right? And one of the reasons for this is that there are some tricky things that have been mostly figured out and wrapped up in libraries like networking and graphics, reasonably tricky to re-implement yourself from scratch if you don't understand how they work, and they can be used in a bit of a generic way. And so all that stateful libraries are, right, is libraries that include, that create some long-lived memory and hold on to it themselves, right? So they have some internal memory that they use to manage their state, and you don't necessarily get the same result every time you call a function, right? You might call the same function twice and get different results because internally the library has some memory that it's using to keep track of its internal state. It's totally possible to create stateless libraries that only expose pure functions. That is, they always do the same, have the same output, given the same input, and they don't have any side effects. More and more libraries and APIs these days are stateful. They include this whole blob of memory on their side that you don't necessarily have access to, or the API that you use to access it is very poor. And this kind of thing almost by definition leads to multiple source of truth problems, right? You end up always needing to duplicate data in your user code that exists somewhere in private inside the library. And I'm going to demonstrate a couple of ways that has had an enormous effect on the quality of software overall. So the case study that I'm going to use is the way that the browser works, right? So inside the browser, there's an API that we use to drive the graphics, display things on the screen. That's called the DOM, or the Document Object Hierarchy, the Document Object Model, rather. It's a stateful hierarchy of node objects, so it's a big tree. You've probably seen it represented as HTML. So you have an outer HTML tag, inside that you have a body, inside that you have potentially a whole bunch of different tags of divs and titles and whatever. So you essentially mutate this giant stateful object, which is stored in the browser. And those mutations that you do cause images and shapes and text and things like that to be rendered on the page. And I think one of the reasons that the browser has been so incredibly successful as a programming model is because it's so accessible, right? As a brand new developer who's never done any programming before, it's quite a thrill to be able to go to google.com and to type document.body.style.background, just, mutate the body background and set the color to red and, watch Google turn red. That makes you feel very powerful that you're able to modify things in front of you and see the visual result. We love doing stuff that has instant feedback, and I think that's one of the reasons why the browser has become very successful as a way for programmers to get started. But here's the huge problem. The browser, as we know it and as we build front-end applications in it these days, is actually fundamentally non-fit for purpose. And the main reason for that is because the state of the DOM is almost by definition all derived data. Right? And if you remember that earlier on in this talk, I was mentioning how saving derived data is a way to create multiple sources of truth, and you end up having bugs because you forget to update your derived data, right? The browser forces us into this model by design. So I'll demonstrate how that kind of thing occurs. Like, say, our horrific bright red Google page that I showed you before. Imagine for some reason Google decides that they want to use this kind of style whenever there's a server error. So if you type something into google.com and press enter and one of the servers is down, they want to turn the background red, right? Here's the problem. In order to do that, you need to mutate an object that's stored inside of this stateful library, inside of this stateful API, which is the DOM. You need to mutate the background and set it to this red color. But the problem is, you almost certainly want something in your code that tells you whether there's an error as well, right? Because you might want to do something like disabling the buttons or displaying an error message or sending some analytics event somewhere saying there was an error. And you can probably start to see where the problem is here now, right? We probably want, even if we had just like a page error Boolean, right, in our code on google.com. And that can be true or false. So if we can make a if statement here. If there's a page error, do some stuff, right? Send an error event to some analytics service. You can see the problem, right? We can set page error to true and we can set page error to false. That doesn't have any effect on the document background color, right? These are multiple sources of truth. We have to remember, whenever we set the page error to true, to set the background color to red. And we have to remember that if we set the page error back to false, we have to set the background color back to white. This is creating a classic situation for operator error, or for a programmer to create a bug. And you might think, oh, okay, well, we have multiple sources of truth. How could we reduce it to a single source of truth? Well, the DOM doesn't provide us any other way to make the page background red. So I guess maybe we could try and rely on the data inside the stateful library instead of having our own version of the data. And as I mentioned before, often the APIs to do this are terrible, right? So imagine if instead of an if statement that says, if there's a page error, do something, right? You're looking through the code on google.com, you're an engineer at Google, and you see this if statement, which is like, if the document has a red background, do some stuff. That's crazy, right? No one writes code like this. Not only is it impossible to understand for new engineers, but you have this other huge problem of like, what if someone has a browser extension installed because they're colorblind and it changes all of the bright red to some other color, right? Suddenly your error handling code doesn't work, right? It's crazy. It's not possible to expect that we would rely on rely on the data that's not fit for purpose inside the stateful library just to try and get to a single source of truth. And so we create multiple sources of truth and then we have bugs. Another kind of classic example in web applications, if you've ever done this type of development, you have an array of products that you return from a server or something like that, and you have the products displayed in the DOM, so you call render products and it inserts, 3 divs with 3 bunches of text inside them. This is multiple sources of truth immediately. If you remove an item from your products array, it's not going to remove it from the interface. If it gets removed from the interface, it's not going to remove it from your products array. Operator error will happen and your UI will get out of sync with your data. It's worth mentioning, like, if you're not convinced by this argument, that React, Angular, Vue, all of these declarative rendering libraries, I think React is probably the most starred project on GitHub, right? Or at least it's close, right? Declarative rendering was literally invented to solve this multiple sources truth problem in the DOM, right? It was literally invented to provide a guarantee that the data on your side in your code would always be represented correctly in the UI, right? They refer to it as UI as a function of state, but what it really is UI as derived data. And this is speaking as someone who has worked, extensively with React professionally for 5 or 6 years now, right? The way that React works is that, exactly as I mentioned at the beginning of the talk about derived data, right? Instead of saving our derived data, we provide a function that allows us to calculate the derived data on the fly. So you can see here we provide a function called createBody, and it returns the actual body tag with the background set to either red or white, red or white, depending on whether there's a page error or not, right? And this seems sensible, and it seems, when I first discovered React, I was like, this is genius. I'm so glad that we can do this now, because I was implicitly feeling the freedom from that multiple source of truth problem. But the insane thing is here that React wouldn't even need to exist if the DOM was designed to actually designed correctly so that it would allow you to have a single source of truth without having to build an entire framework for interacting with the DOM, right? We see this as a really cool solution, but it's a solution to the wrong problem, in my opinion. And so it's interesting to think about, like, okay, well, if the DOM is so fundamentally incorrectly designed, like, why is that the case? Well, remember right at the beginning of the talk, one of the first things that I said was that it's okay to have copies of immutable data that doesn't change, but they won't necessarily stay that way in the long run, right? Remember? The reality is that the DOM was not designed to be mutated, right? JavaScript didn't exist when we first created the DOM. We had HTML and CSS, and there was no way to actually run scripts inside the browser. It was designed as a way to pass visual documents from a server to a client. And so the way that we used to do stuff was you would access a page online and a server would generate the entire page in the correct state from scratch and send it back to your browser. And then when you clicked a link to a different part of the site, your entire page would be wiped and the browser would regenerate a whole other page from scratch and send it to you, right? this model meant that the DOM was immutable, right? Because you never changed it. You only deleted your current copy and requested an entirely new copy. That's how you made changes, right? So we never had to deal with the concept of mutation. Mutating a document is a new thing. Got brought in by JavaScript and has evolved into this insane beast that it is now. So it's really interesting to understand that this was not necessarily any one person's fault. It's just like, this is kind of the folly of adding incremental features without thinking about when that new feature is breaking some fundamental promise or assumption about the way that the architecture was designed in the first place. It's fascinating to me to think about how these historical decisions have cascaded, because we're spending, millions of human hours doing, huge complex projects in React and not really thinking about the fact that all of it, we could potentially significantly reduce that if we had not bolted on this inappropriate model on top of something that was designed for something else. So in conclusion, there are a couple of important things to remember I put 5 here. A few things to remember when you're dealing with single and multiple sources of truth. The first one is the most important. That's knowing what data you actually have. Recognizing when something is saved to memory and what that data actually represents. Are there two things in your data that are the same? If so, try and combine them together and reduce them down to a single reference, right? Second thing, be aware of derived data. Sometimes derived data doesn't look at all like the source data, but you have to be aware of data dependencies. When one piece of data directly depends on another, right? Try not to save the derived data. Try to calculate it on the fly if you can. Be aware of all the rules around pass by value, pass by reference, closures, variable capture, that type of thing, because it can bite you in surprising ways when you think that you have a single source of truth, but you actually have multiple, or the other way around. The fourth thing is just really beware of stateful libraries. Be aware when a library that you're using is storing some memory and doing its own kind of calculations on that internally. What you want to always aim for is libraries that are basically just a file full of pure functions that you could copy paste into your code base and use that way, that you don't have to access as like this blob. And the last thing is just to remember that immutable data, while it's sometimes tempting to duplicate immutable data for convenience reasons, it isn't guaranteed to stay that way in the long run. So you might have a DOM-like situation where something that you fundamentally assumed wasn't going to change is suddenly starting to change, and as a result, you have all these bugs. Thanks for persevering through this long talk. It's something that I think is really important to understand, and thinking about this stuff more deeply, I think, has helped me to become a much better engineer. And of course, I'd love to chat to you about this kind of stuff if you have any feedback, because it's endlessly interesting to me, and I love thinking about the fundamentals of engineering in this way.